class. Let's pick up on page 54. We will finish 2 more topics in section 1.5. The first topic being the average rate of change of a function. So if you do continue on next year and find a calculus class or maybe later in college, this is a very important topic. The average rate of change of a function. Here's this function, it's a curve, right? And the average rate of change is the same as the slope of a line through 2 points. We call that a secant line. That's not so important. But the way that we find the average rate of change, if you look at this equation, it's similar to, it's exactly the same as the slope equation. Remember that f of x is the same as y. So here's our y sub 2, here's our y sub 1 over x sub 2 minus x sub 1. Let's take a look at example 6. Find the average rates of change of this function, x cubed minus 3x, from this point, x sub 1 at negative 2 to x sub 2, negative 1. So we need to find the corresponding y values at those 2 points. So first we're going to find f of negative 1, which is 2. How did we find that? We put in negative 1 here. Cubed is a negative 1. Minus 3 times negative 1, which would be a positive 3. So 3 minus 1 is 2. The same with y sub 1. Y sub 1 would be when x is negative 2. Negative 2 cubed is negative 8 plus 6, which is negative 2. So y sub 2 minus y sub 1, double negative 4, all over x sub 2 minus x sub 1, which is 1. So hopefully that's clear. So this would be the average rate of change. So along a curve, the rate of change is the derivative of the curve. That requires calculus. Right now we're just finding the average rate of change between 2 points. So again, finding an average speed, it's similar. We just find the y values or the functional values at the 2 points over the change in the x's, or in this case it would be the time. That's the independent variable to find the average rate of change. I would encourage you to read through this. All right, the last topic in 1.5 examines even and odd functions. And here are a couple of tests. An even function is for each x in the domain, f of negative x equals f of x. Oh, that's interesting, isn't it? So what's an example of an even function? Well, let me show you an example right over here. If we have y is equal to x squared, then if x is equal to 2, y would equal 2 squared, right? Or 4. And what if x is equal to negative 2? Then y is equal to negative 2 quantity squared, which is also 4. So f of x is equal to f of negative x. That's what this means right here. This is an even function. Let's take a look at the graph of y equals x squared. Hopefully you're familiar enough with it now. It's a parabola. So another test for even functions is that even functions are symmetric with respect to the y-axis. So just looking at the graph, we can tell this function is an even function. So the value at 1 is equal to the same as the value at negative 1. It's symmetric with the y-axis. Also look at the degree of this function. The degree is 2. 2 is an even number. So that indicates to us this is an even function. An odd function, similarly, if you change the number value, you would get the opposite value of the function. So f of negative x is equal to negative f of x. Let me show an example of an odd function. Y is equal to x cubed. If x is equal to 2, then y is equal to 2 cubed, which is 8. If x, let's change change it to its opposite, y is equal to negative 2 cubed, which would be a negative 8. So f of x is equal to negative f of negative x. F of x is going to be the opposite sign of f of negative x. So that's odd. If we look up here at this paragraph, a function is odd when its graph is symmetric with respect to the origin. So that actually we call rotational symmetry. If you were to pivot this graph 180 degrees, it would look exactly the same. So it's symmetric about the origin, and that is an odd function. Also, let's look at the exponent. The exponent here is 3. 3 is an odd number. So this whole function is an odd function. So I am going to show you a shortcut on how to determine, without a graph, whether a function is even or odd. So even functions have all even power terms. What about this? Y is equal to x to the 4th plus x squared plus, 5. Degree 4, even. Degree 2, even. Degree 0, even. So this would be an even function. We could even put, doesn't matter what the coefficient is. It could be negative 7x to the 4th plus 3x squared plus 5. This is still an even function. We don't care about the coefficients. We only are caring about the degree of each term. Now, if you were to say y is equal to x to the 4th plus x to the 3, do you see how we have an even exponent and an odd exponent? This function would be neither even nor odd, which is true with a lot of functions. They're neither even nor are they odd. So the same rule applies for odd functions. Every exponent must be odd. So we could have 4x cubed plus 6x. Degree 3, degree 1, both are odd exponents. This would be an odd function. Again, it does not matter what the coefficients are, even though they're even numbers. That doesn't matter. What matters is the degree of each term. So if we look here at the checkpoint, degree 0, degree 1, this would be neither. Example B, degree 4, degree 2, degree 0, even. And this example, degree 3, degree 1 would be odd. If you are asked then describe the symmetry, no symmetry, an even function, so it would be symmetric with the y-axis, odd, symmetric with the origin. And that takes care of 1.5 part 2.